Okay. So far we saw, I mean there is a slight nuance, there is a slight change. Yeah, question. Yeah. No, why do you think independence should lead to better ERM? So it's just a model choice. See, you still remember that the fundamental question that you are trying to answer is what is the underlying distribution that is generating the data. So everything is a guess in the sense that you make an assumption that this has this functional form and estimate. All that we are doing is we make a guess about what the underlying distribution is and estimate its parameters. Now any transformation on data that you do is implicitly making an assumption. See again, if you are using squared error loss as loss, you are already making an assumption that your data is Gaussian, or rather the underlying distribution is Gaussian. All that you are playing with is the mean of that, which is a function of this. Now there is no reason why you should believe that of course learning a good transformation would definitely aid, but what is a good transformation? It is only post fact, right? So there's no there's no preemptive way of knowing what a good transformation is. However, suppose your transformation is such that they can estimate any function to arbitrary closeness. You know what I am saying, right? So just like GMMs. Suppose what your question is similar to asking what should be the distributional assumption that I make, okay, when I am solving the maximum likelihood estimate. I mean, every model is, I mean, as I keep saying, no, every model is a bad model. Some of them are useful. So now the question is which of them is useful. You choose a model that is expressive enough. So what do you mean by being expressive enough? If the functional form is general enough to estimate or approximate any function to arbitrary closeness, that's an expressive enough model to work with. Which are neural networks? See, why are neural networks the go-to choice for machine learning today is because of this particular reason, is that they are the transformations that are that can be mathematically proven to estimate any function to arbitrary closeness. It is called universal approximation theorem of the sigmoids that we will see later in the course. That is why you make such a choice. Hmm? No, 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 I did not make that statement. I just asked you, if you make a GMM assumption on the class conditional density, what happens to the ERM loss function? I did not answer that question. I did not say that neural networks are equivalent to that. In fact, neural networks with a particular type of activation function called RBFs can be shown to be equivalent to GMMs, not all. Okay. Okay, so let us look at any other question on linear models. Yeah. Only if you assume, if you assume that your loss function is squared error. Yes. No, what do you mean by that? Correct. No, no, even then, not necessarily. The h function will have a scale, that's it. The h theta function will just have a scale to it, that's it. Yeah. Okay, so let us look at this slight modification that we have to do in the framework to accommodate the classification problems, right? Classification problems are D is xi comma yi, and by the way, did you note that I have been interchanging small n and capital N? Yeah, so I just noticed it. It's the human error. See, whenever I write that, I'll write that as 1 over n, right? So that's okay. It's now xi is in RD and yi is in, right? In this case, how do you design your h function? See, the h function should be from x to y, correct? Now if I make my h theta of x to be theta transpose x, then the range space of this h function does not correspond to the other random variable, the label random variable that we have. So I hesitate to call it label, you see, you know why, okay? Yeah, so still let's label it as a label. So the label random variable, so we'll have to ensure that the ranges match, you know, how do we do that is the question. Hmm? Now we'll take, so basically what is done is h theta of x, so we'll say with this the range space of h theta of x won't be y. So now what do we have to do? Just do a composition. So you make h theta of x to be equal to some function sigma of linear function of theta, okay, where sigma is 1 by 1 plus e power sigma of t is 1 by 1 by 1 plus e power minus t. Now sigma t, right, is bounded between 0 and 1. You want a name for this function? Yeah, it's actually, yeah, so call it sigmoid function if you want. I don't want to call it sigmoid function because typical definition of sigmoid function, I mean that this guy Seibenko gave in his original paper on neural networks, is that any function that asymptotically goes to one right side and goes to 0 in the left side is called a sigmoid function. Does not matter what happens in between, okay. But yeah, so this is also one of the sigmoid functions because at the limit of t equal to infinity it goes to 1, at the limit of t equal to 0 it goes to 0, right, but it is bounded between 0 and 1, that is all we need, okay. So now this is you make your h of h theta of x to be sigma of theta transpose x, and by the way you can do this for a generalized linear model as well, right, it can be sigma of theta transpose of phi of x as well, anything that bounds it between 0 and 1. So this is for the case of binary classification. So how do you decide finally? So your final classifier, so what do we call it? We call it h of x is equal to, so class 1 if h theta of x is greater than some tau 0 otherwise. Tau is a hyperparameter. How did I, no, h theta itself I defined as sigma of theta transpose x here. Yeah, is that okay? So this is how you design the final classifier for the case of binary classification. So what do you do for k class classification? Let us define that. So first define h theta of x to be equal to, now theta times x, okay. So let us write down the dimensions first. X is in Rd and y is in uh, yeah, this counting from 0 problem is so difficult for me. Yeah, so it has k classes, okay. So now we define h theta of x to be theta times x. Now theta is a matrix, okay, it is a matrix of dimensions. So this is a column vector, right, which has d rows and 1 columns. This should be k rows and d columns. Is that all right? So what is happening is that, it's correct, no, you will get a k cross 1 uh, vector. Hmm? Now how many parameters? Okay, so too many x's are here. Hold on. See, I already told you, right, in the beginning of the course I will run out of alphabets. Okay, this is my model. Now what? Now what do we do? What do we need? Our final classifier has to give me a number, or give me a class, or give me a label between 0 and 1. And how do we represent a k class discrete vector? Do you remember the one hot representation, right? So we will have to transform this into a one hot vector. Okay, so now the goal is transform a k dimensional real vector into one hot, into k dimensional one hot vector, right? So how do we do this? So suppose uh, V is a vector in Rk, okay, then define a function called softmax on V. How do you define this? So softmax of V, the jth dimension of that is given by e power Vj divided by sigma e power Vj over j. Okay. Now this is the jth dimension of the softmax. Now if a vector z is equal to, or zj is equal to the softmax of the jth dimension, then the vector z, what will be the dimensionality of vector z? K. Oh, yeah, that's okay. Yeah, the reason I said it O was we started from 0 to k minus 1, right? So this is 1 to k. So please be aware of that. So why would this be k dimensional? Because V was a k dimensional vector. We took every dimension of uh, k, right? Every dimension of V, and we subjected this to this particular function, right? So now we get a k dimensional vector. So it can be seen that all zj, right, they are bounded between 0 and 1, okay, and they sum to 1, okay. Now what should we do here? Okay, let me write it maybe later. So in the context of linear models for k class classification, so make your h theta of x to be equal to that is it. You get it? Now the range of h theta of x is You see this? Come again, what happened? Huh? What is a set? Huh? Oh, you want to write it that way? Okay, fine, no problem. See, it's a, yeah, it's a k dimensional one hot vector. That's what you meant. Once you transform it, it's a k dimensional one hot vector. That okay? So then what would be now the final classifier? Softmax will give you a vector that is between 0 and 1. In fact, to be precise, the range of h theta of x is not this, it's actually, yeah, this, right. Now how do you choose? What is the final classifier? I mean, that's your choice. You take the max, you take the second max, you take the best of two, and then whatever, right, that depends upon what the final classification is. Okay. Now these two that I just talked about, right, these two have a name. These are called logistic classifiers or regressors, whatever you want to call it. Logistic regression. This is what logistic regression is all about. Okay. Hmm. Oh yeah, it does matter. The question is in these two class classification problem, right? We have this tau. How how much does it matter? It matters a lot. If you have not watched the tutorial, you have to watch the tutorial. There is something called receiver operating characteristics or ROC. Okay, change the tau, the performance of the classifier keeps changing, and you can trade it. And there are two types of errors: the false positives and false negatives, right. So we have not talked, I mean, I'll mention it later, maybe in the next class, but I think the tutorial has already been done. If you have not looked into it, please look into it. You will, to answer your precisely your question, right, how much tau contributes to the final classification performance. By the way, I've still not told you how to evaluate an estimated density function, right, or an estimated h. We are only talking about estimating h. How to evaluate how good or bad it is, I have not told you about it. I'll talk about it in the next class, or maybe the class next after that, when we talk of bias variance decomposition and generalization. I'll deliberately not told you that yet. We'll come to that in a while. Now we are just building the classifiers. We'll see how to evaluate it in a while. It depends. So please watch the tutorial on that. Okay. Okay, so this logistic regression. So there is one other important piece here, right? So suppose we are solving or looking at logistic regression, right? So how does ERM look like? ERM with logistic regression. We have theta star to be equal to argmin what is this? This is soft max of theta times x minus y. And please note that this y has to be again a one hot vector. All of these y's have to be one hot vectors. In the case of k class classification, the generally the way the data comes is that you have some data which is your image or anything, and the corresponding label. There are k of them. You have to transform that, or you have to represent that as one hot. Otherwise you can't solve this optimization problem, right, because the dimensionality will get mismatched. Do you see what I am saying? For instance, if your data is like an image and three classes, diseased, not diseased, what can be the other class? I don't know. Yeah. See, did you look at the pun? The third class is I don't know, which means I as an individual may not know what the third class is. It may also mean that the third class itself is I don't know. I don't know if you got the joke. There are too many nestings of I don't know that's happening. Anyway, so you have those three classes, you will have to transform that into one hot representation, otherwise this you can't take the difference between these two vectors, right? You do this. Now the question is, can you differentiate this and put to 0 and get a closed form for theta as we were getting in the previous case? Can we? We can't. So the above optimization problem cannot be solved analytically. Then what do? We will have to solve this optimization problem to get the theta, right? We cannot solve it analytically, what do? We solve it numerically, right? So so you can use any of your favorite numerical differentiation technique, okay? Typically it is solved using first order gradient descent methods. Even models that are as big as GPTs, right, which are billions of parameters, are still solved using first order gradient descent. Now, for all the optimization theory that we talk about and and learn, right, the conjugate gradient methods and second order methods, you know why? Because these models are so huge, the state of the art models are so huge that if you have to resort to any second order method, you will have to invert that Hessian matrix. If you are having a 70 billion parameter theta, then 70 billion squared is the Hessian, and inverting that matrix is impossible. So first order gradient descent is all we use. So just for the sake of completeness, I am assuming that all of you know what gradient descent is, right? But just for the sake of completeness, I will talk about gradient descent, right? So let us just quickly look at gradient descent. So suppose we have a function L theta which needs to be optimized. So numerically what you do is gradient descent. So okay, before that we will have to write this. So typically this L theta, okay, uh, typically, right, most of the cases, at least in the cases of ERM, right, this is our empirical risk. L theta is our empirical risk. So this will be, oh, why don't I just write it as no, R cap itself for empirical risk is a scalar function of parameters theta, right, parameters theta which are vectors, which are in some RP. This can be huge. Today this P is 70 billion, 70 billion, right. So some vector scalar valued function of a vector variable. So what we want to do is we need to optimize R cap, okay, with respect to theta. So in gradient descent, so does it iteratively as follows. So start with initialize theta naught, okay, then you make or till convergence, so do the following. You have theta t plus 1 to be theta t minus some alpha, which is a scalar, times the gradient of this particular function that we are optimizing, and this gradient is chosen with respect to theta. So please note that if the dimensionality of the gradient is equal to that of the variable upon which we are optimizing, no. Therefore, gradient of r cap theta with respect to theta will also be in rp. So, gradient is also in rp. That is it. This is gradient descent. Now, why should this work? I can always write this convex curve and say that, oh, it is the direction in which the derivative is the least and all that, right. But we are not dealing with convex surfaces at all, and we are dealing it in very high dimension. So I do not want to write this figure. This is often misleading. So if you look at some of these blogs, right, they'll write this nice convex surface, and some there's a toy, there's a cartoon that is moving in the direction of all that, right. So I don't want to do that at all. The correctness of okay, by the way, for non-convex surfaces you cannot establish correctness of first order gradient descent at all, but this particular functional form came from Taylor series. So what you actually do is express this function as using Taylor series, truncate it to first order, okay, and then write the express the derivative with respect to this, and you get this. Maybe you can do it in the tutorial. Yeah. So gradient descent is not guaranteed to reach to the optimal, especially when the surfaces are non-convex. And most of the surfaces that we will be looking at are non-convex surfaces, right. For instance, this, right, this empirical risk that we are looking at here with the softmax function, there is no reason why it should be convex in theta. We are talking about convexity in theta, right, because the optimization is with respect to theta variable. So here is an exercise that you should do. Write down the gradient expression for this, for a k-class classification problem with logistic regressor. Just write down the gradient equation, right. So typically the way it is solved in computers is that you hardcore the gradient expressions. For this particular logistic model, right, this gradient expression can be hard coded because you can compute the gradient. But for models such as, let us say, neural networks, these gradients cannot be hard coded. You need to use chain rule to do that, because neural networks are composite functions, and that has a name, that is called error backpropagation. We will see that later when we come to neural networks. So it's I mean, as I said, right, even GPTs are being trained using the same gradient descent using chain rule. That's it. In fact, now you see, right, once the framework is set, going from model A to model B is a matter of writing one empirical risk minimization equation. That's it. What's important is setting that framework. What is it being actually done when you are solving ERM is important. In fact, now you can play with things. You can choose your phi. Okay, you can choose your loss function. You can choose whatever model you want. So now you have the entire recipe and framework to solve ERM with any model. Gradient descent is there to optimize, and you have some model. So the just skip my mind. There is another interesting exercise that you can solve. Suppose I change this loss function from squared error loss to what is called as cross entropy, especially for classification problems. What is the underlying distributional assumption that I am making on P of y given x? Try to solve that. You got the question? Maybe I'll write down that loss function, right, for you. So LC, this is between h theta of x and y. Loss is always between h theta of x and y. So here I am assuming that both h theta of x and y, they are both bounded between 0 and 1. That is when I can define the cross entropy, right. I will define it as see, as they say, laziness only will double triple your efforts. I could have written that again. I wanted not avoid writing that, but ended up doing more effort. So this is equal to suppose we are looking at let us say that this is k classes, right. In that case, this is over k, we have h theta of x log of yk, it is a negative here. This is the cross entropy loss. This is, you have to take the kth dimension of this. Take the kth dimension of h theta of x, kth dimension of y, and you compute this and sum it over all possible k dimensions. This is actually the cross entropy. This is the end definite. We have seen the definition of cross entropy or discrete distribution. So that is exactly what it is. You know that this is KL divergence plus the entropy. Cross entropy is nothing but KL divergence plus entropy, right? Because cross entropy minus entropy was what KL divergence is. So KL divergence plus this. We are looking at two discrete random variables here, yk and h theta of x, and we are looking at the KL divergence between those two. That is it. Now the question for you is, suppose we do this, what is the form of p of y given x that we are choosing, okay, that will lead the ML or maximum likelihood estimation to be having this particular form. Just work it out, it is a nice exercise to do. Now you can use this as your loss function, okay, and solve for ERM using the gradient descent. Now you pick a loss function, pick a form for your h theta of x, right, and use gradient descent to build your model. That is it. Okay, yeah. Yeah. For yeah, so you will only have one of them that will survive. You want to do it the other way around? Yeah. So yeah, I think there's a point. What he said is it's better to put yk here and h theta of x here, because if I mean typically yk will be between, I mean it will always be one hot 0 and 1, so log 0 is undefined, so you take yk outside and put hk inside, right, that is okay. Yeah. Okay, so now I think let me just summarize. Now we have the entire recipe now. So given a problem, you have to choose what h function, the form for the h function you want, right, choose a loss function and use gradient descent to solve the ERM optimization problem, you get a model, that is it. So this is from the ERM perspective. So if you want to look into, in fact does not matter, it is just a formulation. So you formulate it as a maximum likelihood estimation or KL minimization problem, or you formulate it as ERM. So there is another interesting question that we should ask. What is the equivalent of map estimate in ERM? It is called regularized ERM. We will see that in the next class. So if you add something called regularization to your ERM, it is equivalent to the ML estimate with a Bayesian prior, which is the map estimate. So regularized ERM is exactly equivalent to map estimate, is what we will see. Okay. So yeah, so we will end today's class here, and in next class I will look at the generalization aspects of it. I look at the bias variance decomposition and evaluating models, and then we look at regularization. Thank you.